Hello everyone. In today's lecture, we'll be covering this topic, pitch dynamic motion of the aircraft, how we can design the control for the pitch dynamic motion, and also we'll have the MATLAB simulation for the same example. And finally, we'll have the how we can design a control feedback linearization control for the lateral motion dynamics of an aircraft. So let's start the example. We'll take the simple example and also we'll the MATLAB simulation code for the same. Let's consider the pitch dynamic motion. The pitch dynamic of an aircraft theta dot equal to q and q dot equal to m by I. So here theta is the pitch angle, q is the pitch rate, and m is the moment, total moment acting on the system, and this is the inertia matrix along pitch axis. So here we can write the pitching moment, which is m, the pitching moment m equal to m naught plus m alpha plus mq plus m delta I. So here, these are the terms we have already defined in the last lecture. And here delta is the only control, which is basically elevator deflection to control the pitch motion. So here objective is the objective design control which make the pitch angle theta to track the desired trajectory theta d. Okay. And also the MATLAB simulation verify the result through MATLAB simulation. So this is the problem statement. Now let's go to the solution part. So for simplicity, we are going to assume some values for this m naught, m alpha, mq, and m delta E. These are the basically aerodynamic coefficient parameters. So those parameters can be obtained through the testing, wheel tunnel testing. So for simplicity, let's assume m naught to be 0. This is the baseline moment coefficient, and m alpha -2, mq equal to -1, and m delta equal to 1, and Iyy we are assumed to be 1 kg meter square. So this is the inertia value of the system. So why you have taken these numerical values? Because we need to do the simulation, MATLAB simulation. To solve the MATLAB simulation, we need to have the numerical values of this parameter. Here, based on these values, our system dynamics, which is defined by equation 1, yields to be theta dot equal to q, and q dot, we can substitute these values in this equation. So we'll get theta dot equal to q, and q dot equal to minus 2 alpha minus q and plus delta E. So delta is the control for this system, and our control objective is theta to track theta d as t tends to infinity, or we can say error to 0 as t tends to infinity, right? So here error you can define as theta minus theta d. So here since we are going to control theta as the parameter, so here we can assume the output of the system is theta. So let's say, let us define the output as the pitch angle, and we can write y equal to theta. Now our primary objective, as you have done in the previous lecture, we have to take the time derivative of this equation till the control appears in this equation. So before that, we can define the error, the tracking error. We can write E equal to theta minus theta desired. So now we'll take the time derivative of this equation, equation 2, taking time derivative of equation 2, we write y dot equal to theta dot. So we'll now check theta dot equal to, if you notice here, theta dot equal to q. So in q equation, there is no control. Only q dot equation, we have the control, delta E. So now we have to take second derivative here, y double dot equal to q dot, and q dot already have here, found here, minus 2 alpha minus q plus delta E. So we can write minus 2 alpha minus q plus delta E. Now, let's assume, so here our main motivation is how we can control this q. So let me write, to linearize the system, the control input, I can write the new control input, chosen as v equal to minus 2 alpha minus q plus delta E. And from this we can write delta E equal to v plus 2 alpha and plus v plus q, right? Now let us define the error dynamics. So we can come up the system into error dynamics form. So let's from error equation, or we can write from E equal to theta minus theta d, we can write E dot equal to theta dot minus theta d dot. We can take the time derivative. And if you notice here, in this equation, there is no control involved. So you have to take that second time derivative. So you can write E double dot equal to theta double dot minus theta d double dot. So theta dot double dot already you have here. this expression. So we can write here. We can write V minus theta d double dot. And from this, we can write, now we have to choose this V in such a way that E is going to 0, right? So if E is going to 0, so we can say theta is going to track theta dz, right? Because E is the difference between the theta and theta dz. So our aim is, so choose V in such a way that E tends to 0 as t tends to infinity. So from this we can choose V as theta d double dot minus k1e minus k2e dot. So this is basically PD control, and where k1 and k2 are greater than 0. Now, if you notice here, if you substitute this V in here, so we'll have the aerodynamics equation, which is basically stable. Now we can write, let us define, this is equation 2 and this is equation 3. Now substituting equation 3 in equation 2, we can write E double dot equal to, we get K2 E dot plus K1 E equal to 0. So this is very easy. So this is, since K1 and K2 are positive, since K1 and K2 are greater than 0, so this equation 4 is a stable dynamics. So stable dynamics means the eigenvalues of this equation are negative. So we can say that E tends to 0 as t tends to infinity for positive values of K1 and K2, right? So now we can find the overall control delta E from this analysis. So what we'll do is we'll substitute this expression here. Okay, so let us define this equation star, for example. Now substitute equation 3 in equation star. So you can find the overall control for our dynamic system, this system, right? Now substituting equation 3 in equation star, we can write the final nonlinear control. We can write delta E as delta theta d double dot minus k1e minus k2e dot and plus 2 alpha and plus q. So this is our overall control for this system. So let us, this is equation 5. So equation 5 is going to stabilize the system which is defined by equation 1, our main system. So and this control going to track theta d as time proceeds. Now let's have the MATLAB code for this example. So this is the MATLAB code for this system. So whatever value we have taken in this example, we have taken the same values here. And these are the dz trajectory of theta and theta d. And this is the initial condition for theta and q, because to solve any differential equation, you need to have the initial values of the states. And this is, we are going to simulate this program for 0 to 10 second. And this is the OD, we have used the OD 45, and this is the function. This is the function here. defined here, and this is the code for the plots, and this is our tracking error, whatever you have taken in the example, and this is the overall control input we have obtained in this equation 5. So this same equation defined here, and this is our dynamic system, what I have taken the dynamic system here, and these are the states going to our function here. And if you notice, this system is controlled using the design control what we have done here. And if you notice here, the actual values, which is the blue line, are tracked to the desired state, desired value of the pitch angle, and this is the pitch rate. So this is how we can simulate our nonlinear system using the proposed design control using feedback linearization concept. So you can, if you have another example on aircraft system, you can follow the same steps to design the control. Now we'll go to the another example for our lateral motion dynamics of the aircraft. So first, let us define the example, what you're gonna solve. So this is the lateral motion dynamics problem example. So let us consider the following nonlinear motion dynamics, lateral motion dynamics of an aircraft given as beta dot. So these are the states are going to involve in the lateral motion dynamics. Y beta divided by mv into beta plus yp divided by mv into p, and yr divided by mv into r plus y delta a divided by mv delta a plus y delta r divided by mv delta r. So here delta a, delta r the control. It is basically aileron and elevator control input, which will design through this feedback linearization based control. And p dot equal to L beta plus, okay, we'll simplify this part this moment. So let us define this part as F1 beta P R. So if you use this, you can write this expression F1 beta P R. This is basically we have taken to simplify our calculation. Otherwise, we have to use a lot of parameters plus y delta a mv delta a plus y delta mv delta. Okay. And here p dot lp l beta and lpp plus lr plus l delta a plus l delta r. And similarly, let us define this is F2 beta PR, and we can simplify this expression F2 beta PR, and we can write L delta A plus L delta R, and find expression R dot equal to, we can write N beta plus NP P plus NRR plus N delta A and N delta R. So these are basically moment coefficients, aerodynamic derivatives, the coefficient L beta P R. So, okay, let me define what are these parameters here. So here, and this whole system we can, this is basically the lateral motion dynamics of an aircraft system, right? So beta equal to, here beta is nothing but side slip angle, side slip angle, and R is roll rate, P is, sorry, R is yaw rate, basically here, yaw rate, P is roll rate, and delta A, aileron deflection, and delta R, rudder deflection, and YB, YP, YR, Y delta A, Y delta R. This is basically aerodynamic derivatives for side force. And so these are the parameters we get from the some testing, and for particular aircraft, these are the data are very important. So most of the industries, they keep these things confidential for a particular aircraft. And L beta, LP, LR, L delta A delta R. This is basically aerodynamic derivatives for rolling moment. And in beta, NP, NR, in delta A, in delta R, aerodynamic coefficient for rolling moment. Aerodynamic coefficient, or we can write aerodynamic derivatives of for young moment. And here mass, M is the aircraft mass and V is the true airspeed. Now our control objective for this particular problem, and design control. So if you notice here, this system is quite complex because in each equation we have different control part, delta in each equation, delta and delta R in equation. So this designing control for this particular system may be challenging, but we'll make the problem very simplified. So let's work on this. Design control for delta A and delta R such way that beta and R can track beta desired and R desired. So this is our control objective. So here only we are controlling beta angle, beta and R, these two equations. Okay, so we can take these two equations to design the control. So here, let's start the problem solution. Let us define the output equation. So since you are going to use the input-output feedback linearization-based control, so here, since this is our objective, so from this we can find the output equation, right? So output equation Y, let's denote as beta and R. And also we have the desired beta and R. So we can write Y desired as beta desired and R desired. Okay, this is our output. Now, based on this, we can find the error. So based on this, we have E1 we can denote as beta minus beta desired, and E2 let's define R minus R desired. Okay, and our control goal is, our objective is, since we have found error, so we can say E and E2, E1 and E2 goes to 0 as t tends to infinity. So if this condition satisfy, we can say beta can track beta is desired and R can track R desired once this condition satisfied, right? So now we'll design the control and how can do these things. Okay, so here let's start with the first equation, this equation, and we'll design the control, and then we'll come on to the second part. So here, let us define this, the equation number 1, and this is 2. From 1 we can write E1 dot equal to beta dot minus beta desired dot. So if you notice here, in beta dot equation, we have the control here. You see, beta dot equation, we have the control. So no need to go to the second derivative. In the first derivative itself, we have the control signal appeared in the beta dot equation. So from this, we can substitute here beta dot equation. So we have F1 beta PR plus Y delta A by MV delta A plus Y delta R by MV delta R minus beta dot desired. So here our since our main aim is E1 to get 0, so for that we can choose some desired control for E1 dot so that this can be achieved. Okay, so here what we're going to do is let E1 dot equal to U1. So this is basically to control the error. Okay, E1, error E1. And from this, now let us choose E1 in such a way that this can be achieved. Okay, so for that, let us choose E1 as minus K1, E1 minus K2, E1 dot PD control, simple PD control. So now what we'll do is we'll substitute this equation here. So if we substitute here, we can write, so let us define, this is equation 3 and this is equation 4. Now, so here basically in place of U1 dot, we can substitute this expression because U1 dot equal to U1 we have already chosen. So we can write substituting equation 4 in equation 3, we can write minus K1 E1 minus K2 E1 dot equal to F1 beta PR plus Y delta A divided by MV into delta A plus Y delta R by MV delta R minus beta dot desired. Right. So from this expression, we can further write Y delta A divided by MV delta A plus Y delta R by MV delta R equal to minus K1 U1 minus k2 u1 dot minus f1 beta pr plus beta dot dz. So this is, let us define, this is equation number 5. Okay. Now what we'll do is we'll take the second error equation, this equation. So from first equation, this is our, we have received to equation 5. Now we will go to the second part, this part. Okay, the equation 2. So let me write from equation 2, we can write E2 dot equal to r minus r dot minus r dz dot. So in place of r dot, we can write our r dot equation, which is f3 beta pr plus n dA plus n dr minus r dz dot. And similarly, as you have done in the previous part, here also you can choose, let's choose E2 dot equal U2. So which is going to control the error E2, right? So to control E2, we have to choose U2 to be stable dynamics, right? Some error, some control, which is basically going to make E2 to 0 over time. So for that, let's choose U2 as minus K3 E2 minus K4 E2 dot. Simple PD control. Now we'll substitute this U2 here, and this U2 dot we can substitute here, and we can come up the function of this and this part, right, as a relation. So we can write, let us define this equation 6, and this is 7. Now substituting equation 7 in equation 6, we can write minus K3 E2 minus K4 E2 dot equal to F3 beta PR plus NDA delta A and delta A and N delta R minus R dot dz. And from this we can write N delta A plus N delta R equal to minus K3 E2 minus K4 E2 dot minus F3 beta PR plus R dot dz. So now we can, let us define this equation 8. Now from equation 5 and equation 8, we can come up some relation in matrix form. So we can write from equation 5 and 8, we can write y delta mv y delta r mv divided by n delta a n delta r into delta a delta r equal to, we can write the control part, minus k1 e1 minus k2 e2 dot, sorry, e1 dot and minus f1 beta pr plus beta dot dz. And for the second equation, K3 U2 dot, sorry, U2 minus K4 E2 dot minus F3 beta PR and plus R dot dgr. Right. This you can write R dgr. So this is our last term. So from this we can further write delta A delta R equal to, we can write, so suppose this is some B matrix, for example. So it will be B matrix inverse into minus K1 E1 minus K2 E1 dot minus F1 beta PR plus beta dot dgr minus K3 E2 minus K4 E2 dot minus F3 beta PR plus R dot dgr. So this is our nonlinear control to control the dynamics, what we have defined here. This for the system, And this control going to fulfill our mission objective. This is our objective. So this is going to help us to track delta A, beta and R2, beta dgr and R dgr. So this is how we can design the control, linear feedback linear based control for the nonlinear system. And I hope you can design your control for other nonlinear system in aircraft dynamics or any other dynamical system. This is the last lecture for this topic. From next lecture onwards, we'll have another topic on backstepping based control for the aircraft applications. Thank you.